Can you plug in pi over 4?
No.
So what do you need to do first? Can you factor? No, there's not really anything to factor. What can you do now? What are you have very limited numbers of things you can do. So what's one thing?
You can make a table.
No.
Oh.
We're past making tables now. Making tables is your last resort. Yes? You divide what?
You do the
Quotient. No, it's not.
Nope, no derivatives. We're evaluating limits. We're not differentiating. Nope.
Multiply by a factor of 1.
Form of 1. Yeah, so what form of 1 do you want to multiply by? What form of 1 do you want to try multiplying by? How about sine x plus cosine x over?
Sin x plus cosine x.
Yeah, we've done this several hundred times earlier in the class. It's not a new thing. So when we multiply this out, we get sine squared x minus sine x cosine x. Oh, plus, I reversed those, sorry. Sine x minus cosine squared x all over cosine 2x sine x plus cosine x. What cancels? The middle terms do cancel, absolutely. And you're left with sine squared x minus what? Cosine squared x all over what? Cosine 2x sine x plus cosine x. You do the limit as x goes to pi over 4. Can we plug that in yet? No, we can't. Okay, so we tried that. You might then maybe think, oh wait, difference of squares on the top. You factor it and you cancel, and then you end up back at the beginning. Great. Okay, so this doesn't seem to have gotten us anywhere too substantial. What's another thing we could try? You all took trig. What's another thing we could try? What identity? Yes, saying identity is like saying doing algebra. Can you be more specific? Sine x minus cosine x, and what does the denominator become?
Sine x squared.
What's it become?
Cosine x squared.
Is this the right order? Yeah, it is right. Yep.
Probably it's sine x squared.
The top is what? Sine x squared. There's no squares on top, Bill. There's no sign.
I thought it was like
Cosine squared x minus
sine squared x.
sine squared x. We have difference of squares on the bottom now, so what does that become?
Wait, what about these?
Wait, what?
There's also...
It's a sine. No. Okay. What's wrong?
Sine squared x. Minus cosine squared x.
Okay, I'm going straight from here.
Oh.
Okay, I'm now trying. Ready? This is. Oh, sorry, I was not clear. I'm sorry. This is try number 2 because try number 1 ran us into a wall. Okay, so what can you do to the bottom? Nope.
And then 1 plus...
Difference of squares. Good. Excellent. So you end up with cosine x minus sine x times plus sine x, like that. Are we pretty close to being able to cancel something out? We're pretty close. We want sine x minus cosine x. So what could we factor out of? What could we factor out of this term right here? The negative 1. So what do you end up with? You end up with the limit as x goes to pi over 4 of sine x minus cosine x all over negative sine x minus cosine x times cosine x plus sine x. What cancels now? Yay! Those go away. And now you're left with negative the limit as x goes to pi over 4 of 1 over cosine x plus sine x. What is cosine of pi over 4? Huh? Cosine of pi over 4 is 0?
Cosine of pi over 4.
What is cosine of pi over 4? What's sine of pi over 2? Pi over 4. So this is 1 over root 2 over 2 plus 2 over 2, so that's 1 over root 2, which is root 2 over 2. Yay, we're done. So what you need to do to find the point where the tangent line is horizontal,
Take the derivative and set it equal to 0.
and then
Solve.
solve. Yeah.
Yeah,
Does that order of doing things sound familiar?
very much.
What did I tell you to do if you're ever stuck on a problem?
Take the derivative and
Set it equal to 0 and solve. Okay, so this is a example of finding, they're giving you a function, taking the derivative, setting it equal to 0, and that's actually what you're supposed to do. Okay, so what is y prime going to be on this one? Low is?
It's well,
Low is?
Use sin x.
Derivative of the top is? Low d high minus high cosine x all over sine x what?
square.
And you want to know when this is 0, correct?
Yeah.
Yes.
And that's when, the only way to make a fraction equal to 0 is when what is 0?
Numerator.
The numerator is 0. So you want 2 plus sine x times negative sine x minus cosine squared x to be equal to what? 0. So you want 2 minus sine squared x minus what? Oh, there's a 2 in there. I'm sorry.
Yeah.
Excuse me. I got to actually distribute it. Negative 2 sine x minus sine squared x minus cosine squared x is equal to 0. What's negative sine squared minus cosine squared? Yeah, factor out the 1, so you get negative, what is it? Plus cosine squared x, which is what? 1. So you end up with negative 2 sine x minus 1 is equal to 0. So sine x is going to be equal to 1 over negative 2. And what's the inverse sine of negative a half? Anybody remember off the top of their head?
Pi over 4.
Oh, it's like
It's like what? Okay, ready? This is on the record here.
225.
What? 225? Radians. We like radians.
Pi over 2 or pi over 6.
Okay, so far we have 225, pi over 6, or pi over 3. Okay, we're narrowing it down-ish.
It is pi over 3 pi over 6.
Oh, it's
So we have the x values, and there are lots of them. Now we take the original original function right here. Take this original one, and we try to figure out what is f of 7 pi over 6. That's cosine of 7 pi over 6 over 2 plus sine of 7 pi over
6.
What is cosine of 7 pi over 6?
Negative 3. Square power. 3.
Thank you. Good. And 2 plus, what's sine of... Oh, negative
1/2.
1/2. So we end up with root 3 over 2 over 3 over 2, which is root 3 over 2 times 2/3, which is root 3 over 3. So our first coordinate is 7 pi over 6 plus 2 pi n, comma, root 3 over 3. There's your first set of points. What do you have to do to find the second set of points?
Plug in
11 pi over 6.
F of 11 pi over 6. And that's going to be cosine of 11 pi over 6 all over 2 plus sine of 11 pi over 6. What's cosine of 11 pi over 6? Root 3 over 2. Okay. Over what? 2 plus negative 1/2 over 2 over 3 over 2. So what does it come out to be? Root 3 over 3. So we think the other point is 11 pi over 6 plus 2 pi n, comma, root 3 over 3.
Wait, can you just scroll up again? Shouldn't it be negative?
Yeah,
Yeah.
there needs to be one that's negative.
Exactly.
I did say negative.
Ah, I didn't hear it. Okay, I was wondering if someone would catch it. Good. So it is negative. So we think those are the answers?
Yes.
They are. Good job. Differentiate a whole different slew of functions, many different types of functions, but there are many that we actually have no idea what to do with unless we actually have a new rule, and that's going to be called the chain rule. So if we actually try to do this here, if we try to apply the rules that we know already, what issue do we run into? Well, if this is the function, we might have done something like this. X squared plus 1 and raised it to the what power?
1/2.
1/2. And we're like, oh, we know what to do with things out of powers. Well, the power rule only applies to power functions. Is this a power function?
No.
No, x is in the base. X is this a polynomial right here?
Yes. No.
No, it's not.
It's not.
We know how to differentiate any polynomial. Can you multiply that out and turn it into a polynomial? No, because you'll have a fractional power. You'll have a fractional power. This is not a polynomial. The power rule does not apply. The product rule does not apply. It's not multiplying times another polynomial. We might drop the 1/2 to the front, and we will do something like that. But then again, in this right here, what's the problem here? Just as simply as you can, what's the problem? Why can't we just make that L, like, why isn't the derivative of that e to the sine x? Any ideas?
Sine x oscillates.
Yeah, sine oscillate, you know, something more is going on there. It seems like we're close to having a, you want to be able to do this, but do our rules apply? No, we know what the derivative of a to the x is. What is the derivative of a to the x? ln a times a to the x. We know that. Is this a to the x?
No.
No, it's not. It is not, and I don't know why it does that. There it goes. Good. Okay, so here is the new rule that we get to deal with and have fun with. The chain rule. If f and g are both differentiable, what does that mean? They both have known derivatives. And f composed g is the composite of the function. Remember composite functions? You plug one function into the other?
Yes.
Then f is differentiable and f prime is given by the product. F prime of x is equal to f prime evaluated at g times g prime of x. And there's another notation for this right there. dy dx is equal to dy du times du dx. You're mostly going to see this, but you will see Leibniz notation sometimes. So what does this mean? On this function right here, what's our outer function? What function is on the outside?
Well,
What's the outer function?
it's to the 1/2 power.
To the 1/2 power. So you have this right here. Let's call this, let's label this, I don't know, h of x. What's g of x going to be? What's the inner function? X squared plus 1. What is h of g of x? You're
H
taking...
of g of x is 1/2 x squared plus 1 to the negative 1/2 power.
No, we're not taking the derivative. We're taking g of x and we're plugging it inside h of x.
The original equation.
The original equation, exactly. So what we've done is we've taken an equation and we've pulled it apart into two functions. Let's look at what this says. It says, take the derivative of the outer function and evaluate it at the inner function. What's the derivative of h? What is h prime? 1/2 x to the negative 1/2. And what are we plugging into that?
X squared plus 1.
So f prime of x is going to be 1/2 x squared plus 1 to the negative times what, though? Times what's on the outside here? G prime of x. What is g prime? 2x. Can you simplify this a little bit? You get x times x squared plus 1 to the... That is the derivative, correct. Now, if we go back up and we look at, when we originally saw this, what was our tendency? What did we want to do? We wanted to take that 1/2 and drop it to the front. The only thing we need to add in now is you also have to multiply by the derivative of the inside. It's the derivative of the outer function evaluated at the inside function times what? The derivative of the inner function. Exactly, exactly. So, what about these two? They look similar, but they are very, very, very different. Let's look at the first one here. This one. Y prime is going to be, what's the outer function? What's the derivative of sine? Cosine of x squared times what? 2x, correct. You see how I was careful to put there's brackets around everything?
Yeah.
You could write that as 2x cosine of x squared. That would be what I prefer right there. Now what about this one? What's the outer function here? No. Sine squared x is equal to what? Sine x all what?
Squared.
Squared. So what's the outer function?
X squared.
Yeah, squaring. X squared. You could say x squared. That's fine. It's the squaring function. Correct. So what is y prime going to be? 2 times sine x to the first power, right? Because you subtract 1. What's the derivative of sine? Cosine x. So y prime in this case is equal to 2 sine x cosine x. and sometimes you see that written without the parentheses, that's fine, but as long as you're clean and neat, I'll accept different notation, but that right there. Are these very different things?
Yeah.
Yeah, is it really, really, really important that you make sure that those are different things?
Yeah.
Yeah, it really is. So we have all these where you can combine the rules. So you can use the power rule and the product rule together, the power product and chain, power product, chain, and quotient rules all together. They don't exclude each other. Now what about this one right here? What's the outer function going to be? E to the, hold on, e to the what? E to the x. So y prime is going to be e to the sine x, but then times what? Cosine x. Is that really, really important that you add in?
Yeah.
Absolutely. Your homework tonight is right here. And happy Friday, everybody.
No, we have
You do have a quiz on 3.1 to 3.3, but you also have homework on this. Congratulations.